Assalamu alaikum students. I, on behalf of Department of Electrical and Computer Engineering, welcomes you all to our first session for sequential logic design of the subject digital logic design. So let us first see the contents which we are covering in today's session. First of all, we will be having some brief introduction about the sequential logic circuits. What are the sequential logic and what are the sequential logic circuits, how these sort of circuits behave, and what is the difference between the combinational logic which we were studying before and what's new in the sequential logic design. Afterwards, we will be having the examples of latches. Latches are basically the devices that can store a single bit and that can be used as a memory element. And we will be discussing different types of latches. For example, the SR latch, the gated SR latch, and the D latch in today's session. As far as the reference readings and acknowledgements are concerned, we are reading chapter number 5 of the book Digital Design with Introduction to Verilog HCL by Maurice Mono. So we are starting chapter number 5 of the book. Till now, what we have studied that we were discussing about the combinational logic circuits, in which we were discussing that the output is only and only dependent upon the inputs. Whatsoever the inputs are applied on a circuit, the output is generated according to the applied inputs, and these sort of devices don't contain any sort of memory element. So the major difference between the combinational logic and the sequential logic is in the sequential logic we do possess some sort of memory elements, but in combinational logic we are not storing any sort of any memory element is involved for storing any sort of inputs or responses of the circuit. Why these sort of devices are important? Because if you see on a daily life, different sorts of devices, for example, the handheld devices, cell phones, navigation receivers, personal computers, digital cameras, personal media players, and virtually all electronic consumer products have the ability to send, receive, store, retrieve, and process information represented in binary format. So, these technology enabling and supporting these devices is critically dependent on electronic components that can store information. For example, the memory elements. So, all those sorts of devices do have some memory elements in order to process information. So that is the prime reason these sequential logic components are very much important, because these are the components that do possess some memory elements. So the major difference between the combinational logic and sequential logic design is that for the sequential logic we do have some sort of memory elements that are present in the circuit, while those sort of circuits are not available for the combinational logic design. So the output is only and only dependent upon inputs for the combinational circuit, and the examples we have discussed for the combinational circuits in the previous sessions for adders, subtractors, multipliers, encoders, decoders, multiplexers, demultiplexers. These were the prime examples which we have discussed in our previous session. So the major difference between the combinational logic design and the sequential logic design is we do have memory elements that we haven't seen those sorts of elements present before while we were discussing the sequential combinational logic design. So this is new for the sequential logic. We do possess some memory. So let us see what is the basic setup for the sequential circuits. So the sequential circuits basically possesses a feedback path in which the outputs are directly or indirectly fed back and processed as can be processed as the input, and the output at any time instant is basically dependent upon the input and the current state. So we can say that the next output is generated with the help of input and what the current state of the circuit is. That is important in order to generate the next output. As far as the categories of the sequential logic circuits are concerned, sequential logic circuits can be distributed into two distinct categories. Uh, Either the circuit can be synchronous or the circuit can be asynchronous. So what's the difference between the synchronous and asynchronous circuit? The major difference for the synchronous circuit is that the transition to the output happens at the discrete instant of time. So it's not possible that at every time instant the transition to the output is possible. So we've got some specific time frame or time interval or time instant that are responsible to produce the output. So the output is basically sensitive to some specific timed information that is being provided to the circuit. As far as the asynchronous circuits are concerned, sequential circuits are concerned, the transition to the output can happen at any instant of time. So we are not restricting for some specific timing event in order to produce the output as far as the asynchronous circuit is concerned. So whatever the change in the input happens, that is being reflected to the output. As far as this block diagram is concerned, basically the major components in the sequential logic circuits are we have some of the combinational elements, and we have a dedicated memory element that is responsible to store some information, or we can fed back the output that is stored in this memory element back as an input. So output at any time instant is dependent upon the input and the current state or the present state in which circuit is behaving. Whereas as far as the simple combinational logic design, we don't have any sort of memory elements or the feedback path that are available in the circuit. So that is the major difference between the combinational logic design and the sequential logic design. Now let us see what are the synchronous sequential circuit components, and what are the basic qualities that are present in a synchronous sequential circuits. So basically, which we have discussed earlier, that in a sequential circuit we do have some memory element or some clock mechanism so to contain some timing information. So as far as the sequential circuits are concerned, a master clock generator is required to generate a periodic train of clock pulses. Since we are achieving the synchronization process by synchronizing our inputs with some specific event of the clock, so we do need some clock generator circuit that is responsible to produce those clocks, which will later be used in order to achieve the synchronization. So a clock generator is required in those sorts of circuits. So the clock pulses are distributed throughout the system. So these are basically the clock sequential circuits, and most commonly used as far as the memory design is concerned. Uh, no instability problems. We do have some sort of circuit that have some instability problems where output is not stable enough, or we can say that the circuit is reacting in its undefined state or forbidden state. So in synchronous sequential circuit, we don't have those sorts of instability problem, because we are synchronizing our response of the circuit with some particular event or some particular value of the clock pulses that are being generated and provided to the circuit. So the common memory elements that are basically implemented as synchronous sequential circuits are basically the flip-flops, which we will be discussing in our later session. So the flip-flops are basically the binary cells that are capable of storing one bit of information. So just like the latches, they can also store a single bit, but as far as the difference between the latch and the flip-flop is concerned, the latches are basically sensitive to the levels and responses of the input, as far as the flip-flops are basically sensitized to some specific edges of the clock. So in those sorts of circuit, if you are discussing about latches as well as the flip-flops, we normally have two outputs which are normally the complement of each other. So to maintain a binary state indefinitely until directed by the input signal to switch state. So these sort of circuit basically maintains the binary state whatsoever the state they are having, unless and until the supply has been cut off or the circuit is switched off. So they basically maintain the state unless and until the supply is switched off, or we have some new input, so the change in the input that is responsible for the change in the output. So to review or to summarize our discussion, we can say that the synchronous sequential circuits do possess some clock generator that is responsible to provide the clock pulses, and the synchronization process is being achieved by synchronizing our events with some specific events that are occurring in the clock. So these sort of circuits don't possess any sort of instability problem. The outputs are well defined, well stable, and the major memory elements, as an example, we can see that are the flip-flops that are basically the synchronous sequential circuits. So let us see figure 5.2, that is the synchronous clock sequential circuit. The clock diagram is shown in the slide. If you can see that The flip-flops are basically the memory elements that are being used in order to store information or to provide the feedback mechanism for the circuit, or in order to store the current state behavior, so that the next state can be determined. So the flip-flops are basically operating on a clock pulses, and the inputs are applied, and the output of the flip-flop is basically fed back as an input to the combinational circuit in order to determine the next state output. As far as the clock pulses are concerned, you can say that these are the pulses, are the periodic pulses with specific duty cycle, and we can say that with specific pulse width. And if you see the behavior of these sort of pulses, these are basically the combination of some high pulses and some low pulses. This is basically a high pulse for that specific duration, and these are basically the low pulses for that specific duration. So let us start our discussion by discussing our first example for the sequential logic, that are the latches. Latches are basically the devices that are able to store a single bit information, that are also known to be the memory devices or the memory elements that have the capability to store the single bit. As far as its construction is concerned, the latches can be constructed by using the universal gates, NAND gates and NOR gates, which we will be discussing in this slide as well as in the next slide. One important thing, or the interesting fact, is that the latches are also the basic construction block for the flip-flops that are basically also the single bit storage devices. So what is the difference between the latch and the flip-flop is basically the process of synchronization and the behavior of the circuit, or the response of the circuit. So as far as the latches are concerned, the output is dependent upon the input, and the transition to the output can be dependent on the any change in some specific input. So basically the latches are the level sensitive devices. The levels or the change in the levels of the input are basically the responsible factor for the change in the output. As far as the flip-flops are concerned, flip-flops are basically the edge sensitive devices. So the synchronization process is being achieved in the flip-flop by synchronizing our output with some edges of the clock pulses, the clock trains which we are providing within the circuit. Either the circuit is synchronized with the positive edge of the clock, or the circuit is synchronized with the negative edge of the clock. So this is the major difference, because the latches are the asynchronous sequential circuits, as far as the flip-flops are the synchronous sequential circuits. So let us see the first example, that is the SR latch. As far as its name is concerned, this is a latch that has the two dedicated inputs named as set and reset. Let me draw the block diagram for you. So we've got two dedicated inputs. The first is set to be S, because this is the input that is responsible to set the latch in the set state. We will be discussing what the set state is and what the reset state is after discussing this block diagram. So S, the first input is S, the second input is R, and we've got two dedicated outputs for the SR latch. That is the Q, that is the primary output, and the Q prime. These two dedicated outputs are always complement to each other. If the Q is 1, Q prime is 0, and vice versa. We cannot have the same value for Q and Q prime. So two inputs S and R. If Q is equal to 1, which means that latch is storing high level, so latch is set to be in set state. So if the Q is equal to 0, which means that at that specific time frame, the latch is holding a value that is equal to 0, so the latch is in reset state. So whenever the Q value is equal to 1, we can say that latch is in set state, and whenever the Q value is equal to 0, we can say that latch is in reset state or the clear state. How we achieve this? We can implement the SR latch by using NOR gates and NAND gates. In this slide, will be discussing the implementation by NOR gate, and in the later slide, we will be discussing the same SR latch by using the NAND gates only. If we see this logic diagram here, we can see that we are using two dedicated NOR gate. This is, for example, my NOR gate number 1, and this is my NOR gate number 2. Let me label in order to explain the concept. Uh, we can say that the outputs at any time instant, we can say that there exists a feedback mechanism. For example, the output that is being connected with Q, the Q output is fed back. The Q output is fed back to the second NOR gate in order to determine Q prime, and at the same time instant the Q prime is connected to the first NOR gate in order to determine Q at any time instant. So the output is not only and only dependent upon inputs, but the previous information that is been stored in that particular setup. So if the value of s is set to 1 and r is set to be set to 0, the first entry in the function table. So function table is a bit similar to, you can say, that truth table. So the function table is a table that basically determines the functionality of our design of a sequential component. So s is set to be 1 in this particular case and r is set to be 0, then q is set to be 1 and q prime is set to be 0. This is known to be the set state. If we apply 0 0 at any time instant, s is equal to 0, r equals to 0, q and q prime are maintained to the previous level, that is known to be the no operation or the no change state. And if we reverse our input combinations, we set s to 0 and r to 1, the latch is resetted and we can say that it's in reset state. But what if we apply both inputs high? If you see the last combination, that is set to be 1 1. So if you apply 1 and 1 to the circuit, q and q prime are both set to be 0. So in our starting discussion, we can say that q and q prime are always complement to each other. So this is the state that is known to be the forbidden state. So we have to avoid this uncertain state in order to stabilize our circuit. So we can see that this state can be avoided by achieving the synchronization with some clock element while we were discussing the flip flops. So flip flops are basically the motivation for the flip flop is that we have to avoid this forbidden state, and our output states are always definitive and clear at every time instant. So let's see how this circuit will behave. So we have to see the basic functionality of the NOR gate. Uh, Let us see the truth table for the NOR gate. In order to explain our concept, let us assume we've got a NOR gate with two inputs A and B. A and B, and Y is the output. A, B are the inputs in our example, and Y is the output. So the NOR operation is basically the reverse of the OR operation. So the combination of inputs are 0 0, 0 1, 1 0, and 1 1, and the output generated for these combinations are 1 0 0 0. So let us see the first combination, how the first combination is generated. So for that, let us assume that latch is being stored in the set state. So we are assuming, in order to operate the circuit, that the previous outputs at that time instant was Q was 1 and Q prime was 0. So we are applying S equals to 1 and R equals to 0. If we see this truth table, one interesting fact we can see that if we don't know what the previous output is, by observing this truth table, that at any time instant, if any of the input goes high, for example, we can see from these three combinations that any of the input from both the input goes high, the output goes low. So if we don't know the previous state, we can easily generate our outputs by using this fact or this interesting information. But since we are assuming the output, we can say that we can clearly generate our outputs depending upon our assumption. You can assume any other state that is dependent upon you. I am assuming that the latch has been as a latch has been set is already in the set state, and I have applied s equals to 1 and r equals to 0. So how the outputs are generated? If we see that this 1 is being fed back here, so 1 and 1 input is applied here, so the output of q prime goes to 0. This 0 is fed back here to see what should be the status of q. So r was 0 and this feedback path produces 0, so 0 and 0, this combination, this one is being produced. So the latch is uh, already in a set state, so there is no change. The latch is considered to be in set state. So what if we are applying 0 0? Now I'm changing the input to 0 0. It means s equals to 0 and r equals to 0, and latch is already in a set state. Now if you observe the table here, uh, for this NOR gate, we are having the inputs 0 and 0. This 0 was the output or the status of q prime that's already stored. So the next state output, the next output that has been generated by applying this 0 and input 0, that is 1. Now this one is fed back here, and if we see the truth table, in that particular case where one input is 1 and another input is 0, the output is 0. So there is no change in the status of the output. So we can say that whenever we apply 0 0, the latch remains at no change state or no operation state. So let us change now the inputs in such a way that R is defined as high. So in that particular case, the first NOR gate produces 0. This 0 is fed back to the second NOR gate, and the second NOR gate produces 1. So in order to ensure that q should remain at 0, this one we can cross check that this one is fed back here instead of this 0. So the output of the first NOR gate still remains at 0. Now in this particular case, the latch is set to be in reset states because q is equal to 0. Now after this combination, if we apply 0 0 again, the output of the latch is not affected, or we can say that that remains on the previous level as we have seen when the latch was in set state. So there is no change in the output. The latch will remain in that reset state. Another important input, that is basically 1 and 1. Let us see if we apply 1 and 1 here. So if we started from our discussion from the first NOR gate, the output is switched to 0. This 0 is fed back here to the second NOR gate. So this NOR gate produces 0, and this 0 is fed back here to see any change in the output depending upon the previous input that remains on a 0. So both inputs in both of the outputs in this particular scenario are equal, which is not the possibility because we have already defined that q is always opposite to q prime. So this state is known to be the forbidden state or invalid state. This is forbidden or invalid state. So I hope so from this discussion now the functionality of the SR latch is clear, which we have got two inputs S and R. If the latch is storing 1, we can say that latch is in set state, and if the latch is storing 0, we can say that latch is in reset state. Coming to the next slide, that is the implementation of the SR latch by using the NAND gates only. So this is the representation of the SR latch. This logic diagram basically represents the operation of the SR latch by implemented in the NAND gates. So there's not a big difference in the circuit except that instead of NOR gates we are using NAND gates, and same sort of feedback mechanism is used which we were using before for the SR latch implemented with NOR gate. As far as the placement of the inputs are concerned, that is basically important. So the placements of the input for these NAND gates are basically reversed. If you see the previous implementation, the placement of these inputs were reversed, and the functionality is also reversed because we are using now the NAND gates. So we can say that we can also call this latch as S prime R prime because the low at the output at the value of S and R basically determines our output. So if we can see the function table, we can clearly say that if we set S to 1, let us look at the first entry of this function table. If we set S to 1 and R to 0, the Q is defined as 0 and q prime is defined as 1. So q is basically following s prime, so and q prime is following basically r prime. So in that particular case, if the value of s is set to 1 and r is set to 0, the latch is considered to be in reset state. So that is the difference between the latch which we have already discussed, that is implemented with NOR gate. So the functionality is basically reversed. Same is the case with the same inputs. If we apply 1 1 here at any time instant, the latch is considered to be in the no operation state, whereas the 0 0 triggers the latch into the forbidden state, which we can verify this by applying these combination of inputs at any time instant to this logic diagram in order to explain our concept. So I hope so the functionality of SR latch with NAND gate is also clear to you. Now let us modify our SR latch with bit enhancement to introduce some more control. In a previous session, we don't have any sort of controlled input that is responsible to control the behavior of our circuit. So in this particular example, that is the same example of the SR latch implemented with NAND gate, but with an enable input. So whenever the circuit is enabled, the circuit is behaving in the normal mode of operation, and if the circuit is disabled by setting enable equals to 0, uh, then in that particular case, the response of the circuit should remain at the previous state. Whatsoever the previous state is, the response should be hold to that. So that is considered to be no change. So the inputs cannot change the status of the output. Whatsoever the change of the input is, that is not reflected at the output because the latch is disabled in that particular case. So if you see the logic diagram for this particular implementation, this is the same setup. That has been used. This is basically our same old latch, SR latch, that is implemented by NAND gates. These are the two digital gates that are responsible to provide transition of these S and R to our latch. So this latch is known to be the gated SR latch. So these gates basically control the flow of the inputs to the circuit with the help of this enable input. So whenever we've set the value enable to 0, in that particular case, whatsoever the value of S and R is, in that particular case, the output remains at no change state. And if we set the value of enable equals to 1, in that particular case, let me see if we have some, yeah. So if we set this enable equals to 0, in that particular case, we are getting 1 and 1 here, which is forcing this setup to be on no change state. And if we set the value equals to 1, in that case, the output of this NAND gate is equivalent to S prime, and output of this NAND gate equals to R prime. Now the transition in these S prime and R prime are responsible for the change in output for Q and Q prime. So if we set the enable to 0, the latch is configured in no change state, and whatsoever the status of S and R is, the outputs are not changed with the change in S and R. So in order to reflect the change in the output or to set the latch in set state or reset state, we have to enable this device, and we have to set this enable input to 1. So whenever the enable input is set to 1, now S and R are reflected in their complemented format to the rest of the circuit. So now these are the inputs that are responsible for the transition of the output. So whatsoever the status of S and R is, now these basically determine the output value for the Q and Q prime when enable is set to 1. So this is the difference between the previous operation and the new operation, or the operation of the gated SR latch. Gated SR latch gives us much more control uh, as far as the normal implementation is concerned. So we are using some additional resources in order to get more control on the circuit. Whenever the circuit is enabled, then the circuit is behaving and reacting to the inputs, and if the circuit is disabled, then the output should be hold to the previous value, whatever the previous state of the circuit is, that is the no change state. So this functionality is basically defined in the function table as well. Another important observation which we can see from this implementation, and the major difference between our normal implementation and the previous implementation, is that there is not a possibility uh, for the outputs to be set to equal. In the previous cases, either we are implementing the latch with NAND gate or the NOR gate. When we were discussing SR latch, there was a possibility when inputs were equal to 00 or 11. In that particular cases, the outputs are equal, either set to 00 or 11. That is not defined to be the invalid state. So how to avoid this invalid state or the forbidden state? We have to switch to another mechanism that is basically similar to the gated SR latch. So whenever if we eliminate the possibility of the same inputs at any time instant, the outputs cannot be same for the rest of the combination. So the D latch is the reason of the construction in which we can avoid this forbidden state or the invalid state, because this sort of circuit only has a single input D. The value can be 0 or the value can be 1. So how to achieve that? Uh, the D latch is also similar to the gated SR latch. There is not as much difference as far as the functionality is concerned and the operation is concerned. Whatsoever we are doing is that we are using this NOT gate this NOT gate in order to ensure that whatsoever the inputs applied at these gates, this first NAND gate and second NAND gate, are always complement to each other. So we are eliminating those cases that can be produced by applying same inputs at any time instant. So any undesirable conditions of any indeterminate or intermediate states in RS flip-flop is avoided by using this setup. And whatsoever we are making changes, we are only using an additional NOT gate in the gated setup. So D is basically our data line or the input line that is responsible to produce our output, and our outputs are sensitive to the D here. Whatsoever the value of D is, the output is following that particular case. And when enable is equal to 1, Q basically follows D. So if you see the function table here, if we set the enable to 0, whatsoever the value of D is, there is no change state. And if we set enable equals to 1, now this D value is reflected at the Q output. So if we set D to 0, Q equals to 0, that is to the reset state. And if we set D equals to 1, Q is equal to 1, that is in set state. So we can easily say that by this discussion that the next output that is being labeled as Q of D plus 1 is equal to D, or we can say that Q equals to D in that particular case. So this setup eliminates any possibility of undesirable conditions. So let us see the symbolic representation here for the SR latches and the D latches. These first two symbols basically represent the implementation of the SR latch, where the first implementation where S and R are applied to this block. Basically, this is the latch that is implemented with the help of NOR gates, if you remember. So if you see the second representation, that is S prime and R prime, where S and R prime basically that are being shown represented by these bubbles on the input. These are the implementation of those latches of the SR latches that are implemented with the NAND gate. And this is the latch basically that is implemented, that can be implemented with NAND gate or the NOR gate, but that is basically a D latch with enable input and a D input, and Q is basically dependent upon D, that is dependent upon the circuit itself, the construction of circuit itself, either that latch is implemented with NAND gate or the NOR gate. So Q is basically dependent upon D. So till now, this is the end of our class, our first session. Let us summarize what we have discussed in this session. We have discussed the importance of sequential logic, and we have compared the sequential logic with the combinational logic, and we've seen a major difference that in the sequential logic design, we've got some memory elements or some feedback path. And we have discussed that the sequential logic design can be categorized into two categories. Either that can be asynchronous sequential logic design or the synchronous sequential logic design. Then we move to the examples of the latches that are basically single bit storage devices, and latches are basically the example of asynchronous sequential design. And we have discussed the cases for the SR latch, the gated SR latch, and D latch implemented with NAND gate or the NOR gate, and we've seen the basic operation or the operating principle of these latches. I hope so. From today's discussion, most of the things are clear. At the end, please consider chapter number 5 of the book from page 211 till page 217. So kindly go through these pages, and for question answer session, definitely if you've got any ambiguity or any dedicated question regarding our discussion, we can address those questions in our question answer session. Till now, students, goodbye, be safe, and have good health. Allah Hafiz.